Hi. So today we are going to look at some problems that I solved while preparing for tests and what are some common mistakes that I made, and I am using Python as my primary coding language. Let's get started. Count nodes equal to average of a subtree. So the first thing that you come here and you notice is that when you want to, given the root of the binary tree, return the number of nodes where the value of the node is equal to the average of the values in its subtree. So what does this mean? This means that before you are able to check that this node satisfies this condition or not, which is sum of the elements which are its children, divided by the number of children it has. If this is true or not, you have to get done with the left subtree and the right subtree. So everything should be done, and then you can come back and then you can check if this condition is true or not. So you need the sum from the left side, you need the count of nodes from the left side. Similarly, from the right, you need the sum and the count of nodes, and then you can check and calculate if this node satisfies that condition or not, and if we should add this to our answer. So this is where the concept of recursion and backtracking comes in, that you can't do anything unless and until you do it for the children, right? So that is where that comes in. That's how you know that you need to use recursion or backtracking. So we used recursion and backtracking in this one, and it's a very simple solution. It's also very important to take care of base cases, and it's very easy to forget about them in an interview. But yeah, it is very important to be aware of that one thing that you usually forget. So base cases important. Being able to explain what the time complexity would be, that is also very important. Let's just keep this here. Cool. There's another one called largest divisible subset. Given a distinct set of positive integers, num, return the last subset that every pair of elements in the subset satisfies. Either this condition or this condition. So this is very standard DP problem of the LIS pattern, longest increasing subsequence. So that is something, that is a concept that you'll have to know in DP before you solve this problem. I studied it from Striver's SDE sheet. So you can look at that if you want to understand the concept. Here, when I was solving this question, right, one thing that I made a mistake in is assuming that the array was sorted, which it is not. Even though these examples are showing you sorted array, it does not mean that it is sorted. So that is a very important thing. Like whenever there is a question with an array, you should always think about, is this sorted? Does this have zero? Like, is this including zero? Does this have negative elements? Does this have positive elements? And all sort of that. Here it's mentioned that it's distinct positive integers, so you don't have that issue here. Also in Python, we don't have int, it's called int min. So we'll be using minus sys dot max size minus one. So make sure to import sys when you're coding. Rest of it is almost the same as what Striver has explained in his video. But one mistake that I made while doing this was in like trying to do it fast. I appended this integer to the path instead of appending the nums of maxify, that is the value in the array, I appended the index. So these are mistakes that you cannot be making in an interview, and people will judge you on based of that. So take your time, make sure that you're actually writing correct code and not just skimming through it. Like it works in your head, but it has to be written correctly on this one. So this is one mistake I made. I was a very silly mistake. That's that. Next we have oh no. Okay. Yeah, so all this time when I was talking about largest divisible subset, I meant this tab. Um, yeah, so this is what I was showing there, that whenever like what two things. This is the initializing the answer, sorting the numbers array, and also when you're appending, make sure you're appending the value and not the index. That's it. Let's move on to the next one. Longest string chain. So, longest string chain, you're given a array of words where each word consists of lowercase English letters. Word is a predecessor of words. And if only we can insert exactly one letter anywhere in it without changing the order of other characters to make it equal to words. For example, ABC is a predecessor of ABAC, while CPA is not a predecessor. The word chain is a sequence of words where word predecessor is a predecessor of word and so on. Single word is trivially a word chain. Return the length of the longest possible word chain and the words chosen from the given list of words. This is again a very typical LIS pattern problem. It's already there in Striver's DP sheet. I have solved it mostly from there. But one issue that I faced while doing it myself is writing this function, this difference function. So if the difference is true, like this is like the correct, like maybe we could have done it like equal to true or something, but if the difference, should probably not call it difference, we should call it predecessor. So if predecessor words of I and words of 2, which means that J is a predecessor of I. That's what it means. Yep, that's what it means. So if length of string 1 is not equal to length of string 2 plus 1, then return false. So definitely the difference between these two is going to be 1 and 1 only. So you return a false and then you have two indices. The first to go to the first string, second to go to the second string. So while the first is less than string 1, length of string 1, and the second is less than string 2, and string 1 of first is equal to string 1 of second. So both of them are equal, that's great. Increase the first and the second one as well. Else, just increase the first one. So at the end of this, if the first is equal to length of string 1 and second is equal to length of string 2, that is they reached, both the pointers reached the end of the string simultaneously, then you can return a true, else you'll have to return a false. So there was an extra character anywhere in the string. Might be at the end, might be somewhere else, but it has to be in order. So that's that. Another mistake that I made here is not sorting the words according to their length. This is how you do it in Python. You can also use lambda x colon lambda x colon x equal to ln x, but this is also a little easier. It's like smaller. So if you see this, you will have to sort the words by length because we are making assumptions, right? We are making that assumption if a longer string predecessor is there, then it is like the predecessor for all the strings before that. So whatever J was a predecessor for, and if J is a predecessor of I, everything whose predecessor was J is also a predecessor of I. That's why we are adding this here, right? So this is something we need to keep in mind when we are doing this, and definitely it's very important to sort the words by length, something I forgot and I shouldn't be. So these are the two things, this writing this predecessor function and sorting by length. That's it. This is just writing the lambda function in a different way. That's it. Let's see what else do we have. Longest string chain, we did it. Hmm. Yep. What is this one? Detect cycles in a 2D grid. Yeah, this is something that I was solving recently, and there's a few things that I made mistakes on. Not this. This was correct. Is valid new column in grid. Yeah. So there is this thing about path visited. It's just not visited. If it was it visited in the current path is something that needs to be done. So whenever you're trying to detect a cycle in a directed graph, you need to have this concept of path visited along with the visited array. Let's see where our visited array is. Do we have it? Where is it? For I in range n. So this is where it starts, right? So parent is initialized to -1, -1. And for I in range n and j in range m, if parent of ij is equal to -1, then create a new path and pass it along. And then this basically looks like the DFS array. So maybe we can also convert this to a mm, doubly like a 2D list. This is also fine, but I guess a 2D list would be more optimal. So if you see, this is the different changes in the rows and columns. And first, it checks if it is valid, if the new cell's value is equal to the old cell's value. Next, it will check if this is visited. If it is visited and the parent is not this one, then you have to return a true. This is a cycle, you need to return a true. And if it is not visited, then you need to store this, like you need to update this, and then move on from this one. So created like a started DFS in the new row, new column, parent and path. So when you pass this path, it adds this, right? So it's like a visited array. I'll be changing this in the future, maybe sometime. This doesn't look very optimal. And if this is the part that I missed, right? So you can't just execute DFS, right? This is not like counting or anything. You need to return a true if any of the DFS returns a true for this one. You need to return a true. That is something that you need to, and at the end of this whole thing, you just mark that as unvisited. That is something that you do at the end. Then you return false. So if I run this, it's accepted. And if I submit this, hmm. So it did get accepted and submitted, but yeah. So that's kind of it. These are the problems that I solved. If we go to something else, like we can paste it here. Can actually let's see what else I have. If I have anything specific. So just for like I'll just be using this space. Share this tab instead because I didn't want to go back. I can't present my personal desktop, but I did want to go through these few problems. So why is the time complexity of heap insertion big O of n? Something that I wrote randomly, but it is not. It is big O of login. So it takes login swaps to take like whatever element you put and heapify the heap, like maintain that min heap or max heap property. So it's login. This is incorrect. Isn't heapify applied every time we push a new element into the heap? Yes, that's correct. We apply heapify every time we push a new element to the heap. So basically, if you're pushing n elements, the complexity of the creating the whole heap is n log n. How to implement max heap in Python? Hmm. So what Python gives us automatically is a min heap, and you can use it by using the heap queue module, where you have the heap pop and heap push functions for pushing and popping elements into the heap. Now in like automatically Python actually creates a min heap If you want to create a max heap, you can negate the elements and insert them into the heap. That is something that you can do. And when you pop them, you can just like negate them again so that you get the correct element. Largest rectangle in histogram, one pass approach. So, this is something that I recently solved and also wrote a Medium article on. So, let's say you have a bunch of histograms, right? And then for each histogram, your thing is to, like, how would you know what is the longest span that you have to be able to calculate the max area? So, for one, um, let's say histogram, you go to the left of that height and you go to the right, and whatever is the minimum, like you can keep going till you reach something which is less than it. So you have the left boundary and you have the right boundary. So for each height block, you need to calculate the left boundary and right boundary and multiply it with the value of that height. And you need to get a max of all of these values to be able to solve this problem. Is there a one pass approach? There is, but that's not very intuitive. Um, so we'll let that be. Sort stack recursive approach, very, very important. There's two. So this is like a example of nested recursion where you have a stack, right? And you see, like you just pop an element from the top of the stack and then you call the recursive sort function for the rest of it. Now, when you are coming back, right, after doing this, like you need to insert that element back that you had popped from your stack. Now, when you insert this element back, you check if it is greater than the top element in the stack. If it is not, then you need to insert it in its correct place. You need to pop the top element. So again, you have another recursive function to insert this element back. So that is the concept mostly, and it worked pretty well. It's a very nice problem, I would say. Implement min stack. This is something that would be pretty complicated. For now, I'm using Python's heapq module. In the future, I do plan to, implement a min heap sometime. Yep, that's in my list. Sliding window maximum, DQ. Yep, that's also very, very important. You need to think about it. Like if you want to see like the max element in a, let's say, a sliding window of a certain size k, then you can use a DQ, push all the elements from the back of the DQ. Every time you want to insert something, you just check if it is less than the element at the top of the DQ. If it is greater, then you need to pop from the back and then insert. Also, if it exceeds the size, then you also need to pop from the front. So that's also something. This pop and pop from front and back is also very, very important. Make sure when you're writing the code, you write comments that pop right, pop left, because it's very easy to get confused in Python because we have pop and pop left. We don't have pop right. So some comments always help, and I made a very silly mistake when I was coding this up. So it's better to, be clear and write those comments which help you in solving the problem a lot faster. Next, coming to the number 10 line, maximum of minimum of every window size. Hmm. So again, in a lot of problems, the solution, like the optimal solution, I'll say, pops up right in my head. Like I don't even have to think about it. Like I know exactly what to do because I have practiced it or I have seen problems with the same concepts. What do I think of when it comes to this? So we need to get the minimum. in every window size, and we need to get the maximum of it. So it does, um, okay, yeah. So the optimal approach is not very straightforward. It's like at every element, you go to the left, see the left boundary, go to the right, see the right boundary, and then calculate the window size, the max window size in which that element is the minimum. So you need to get the left boundary and the right boundary for something lower than that. So whenever it's lower, you can't, that's not the lowest anymore. So you have an array, like if the size of the array is n, then you have an array of size n, and each um, element of this array at the index denotes the size of the window and the minimum element in it. So whenever you start for one element, you go to the left, you go to the right, think of the span, and then whatever the span comes, you populate this value in this array that you just created. So you keep going, and once this array is fulfilled, whatever is the maximum in this array is your answer, and that's it. Whatever was empty, maybe it's okay to keep it empty, or you could populate it with the value of array of the last index, because that is what the rest of the unpopulated ones will be. Maximum of, sorry, we got through that. KMP, creating the prefix suffix array. Yeah, this is another one. Being able to create the correct prefix and suffix array is also very important. For the prefix array, we have a mechanism to be able to check if there's a repetition anywhere. Similarly, Rabin-Karp rolling hash, it uses a complex rolling hash. Let's take 26 mod something. So that's a lot. This is something that I need to come back to. This KMP has to be solved from scratch, even though I have done it. Think we need to practice it a couple of times. What I remember from KMP is that it's like string and pattern, and the pattern we create a KMP, let's say LPS, lowest prefix, which is also a suffix, like lowest proper prefix is also a suffix, something like that. So for the first one, it's always 0, and then you keep on going, and you have two pointers, one on the left and one on the right. So whenever the right matches the left, you increase both I and j, and whenever it doesn't match, you just populate a 0 and keep moving on. So something that we need to look at again. Let's look at it right now. Yep, seems like this is a software. But let's look at this, how this has been done. So for in KMP, you have the length of the pattern as M and length of the text as N. LPS, an array is created with the length of the pattern. Then we have J, which is an index for the pattern. Then there's this function called compute LPS array. Let's go there first. So first, the length of the previous longest prefix suffix is 0. LPS of 0 is initialized as 0, as I had mentioned. I starts from 1, and while I is less than M, which is the size of the pattern, if the pattern of I is equal to pattern of length, then increase the length of 1. LPSI is equal to length. So assign that length to LPS and then also increase I. Else, this is tricky. Consider this example: AACA with I equal to 7. The idea is similar to search step. So this So whenever you know this, right, AAA and CAA, like if you know that AA and AA match each other, then you want to start from the last one. So if length is not equal to 0, then length assign length to LPS of length minus 1. Else LPS of I equal to 0 and I plus 1. So this is where the concept of not doing the same thing over and over again comes in. So this first part is same as this part. So like when you know that like the 0 1 index matches with 3 2 index, like prefix and suffix, then you will check this index, like you'll check these three and these three. So that's what you will check. So that's why you don't want to directly detach. So if length is not 0, like if they're not matching but the length is not 0, then assign length to LPS of length minus 1 and then keep going. But if the length is 0, then you need to assign LPS to 0 and I plus 1. Now once the LPS array is computed, it will go from n minus I is greater than m minus j. So if pattern of j is equal to text of I, increase both, great. If j is equal to m, found pattern at index I minus j is equal to LPS of j minus 1. Mismatch after j matches. So if I less than n and pattern of j is not equal to text of I, j do not match LPS of j and letters, they will match anyway. So if j not equal to 0, then j equal to LPS of j minus 1, else I plus equal to 1. Very similar to what we did here, where we assign length to LPS of ln minus 1. Here we are assigning j to j minus 1 and then I plus equal to 1. This is a very important thing. It's like if you know that A like is a, what is this? Yeah, if you know that this, right, these two and these two are matching, then in the next step you will be trying to match these two and then like you'll be trying to match these three and these three. So let's say this didn't match. In the next step you'll be trying to match these two and then you'll be trying to match the first two like these. So if that also doesn't match, like that's where this len equal to LPS of len minus 1 and j equal to LPS of j minus 1 comes in when they don't match. Like if it is 0, then assign it to 0 and increase the index of the text. But if it is not 0, then assign j to LPS of j minus 1 because you don't need to match LPS of 0 to LPS of j minus 1 characters because they will match anyway because you already know. So you reduce your work. And that's why the time complexity of this solution will be big O of n plus m. That's something. Okay, let's go back to where we were on our lead code problem. Okay, and then we'll come back to this Rabin carp after some time. We also have Morris traversal, we have post and pre-order iterative, which is again, so if we think of doing the pre-order iteratively, like you can think of it like when you like, how do you make recursion iterative? You do it by putting it in a stack. So that's what we'll do. We'll put it in a stack. For pre-order, we will need two stacks because we get it in a reversed order and we'll have like it's easier to reverse that stack. Also, for the in order, there's this if stack equal to empty. So you keep on going till the stack isn't empty. That's also there. So when you push, like you keep going left, and when you can't go left anymore, you push the right. Like you take out the node and push the right. So this is the main concept. It's something that you need to like code and like think about to understand. Priority queue in vertical order traversal in binary tree needs level or L vertical and level. So it also needs the vertical and level. It just doesn't need the vertical only or the level only, which is important. And then max fit of binary tree is not what you think. Definitely not what you think. It's like it could be that there are nodes in a level that are missing, right? So you can't just use a formula like 2 multiplied by I plus 1, like length of the like height plus 1 minus height minus 1. You can't do that. You'll have to like calculate the distance between the last node on that level and the first node on that level. And also there is a risk of integer overflow. For that you need to like every time that you are in the on the level the first time, reduce the like just minus it with that very value so that you start from 0 again and not some crazy big number which gets multiplied by 2 every time. So it's 2 multiplied by I plus 1 and 2 multiplied by I plus 2. These are the two ones. Max width of my, okay, peak in Python. This is not peel, this is peak. Peak does not exist in Python is something that I recently noticed. You just need to use a minus 1, stack of minus 1, and that's a constant time operation. For boundary traversal, why pre-order and not in order? It's actually in order and not reorder. And someone mentioned it's probably not possible to do it with pre-order. I'm actually not sure about it. I tried with a bunch of trees, and every time I did it, it gave me the correct order for both in order and pre-order. So yeah. And children sum property, that's something that also involves backtracking. It's that if the sum of the children is less than the current node's value, then assign that to the current node. If sum of the children is greater than the node's value, yeah, this is something I need to come back to. So let's put a cross beside it. Also cross beside this guy and this guy. This is like basically the second version of the revision. Also beside Morris traversal and pre-order and post-order iterative, even though I've done it like n times. And also beside this. Populate the next right pointers in each node. What does this mean? Not sure. Validate BST. Yep, can do it. I did solve this. Size the large of the. So basically, validate BSC has that left. So whenever you want to validate a BSC, right, it needs to be in between certain values. The left should be less than the roots value. The right should be greater than the roots value. This is the main point. You keep on changing this recursively as you keep going, and when like as long as you get return a true, it's all good. Else you can return a false. If each time you see anything broken. Um, Size of the largest BST in a binary tree, yep. From the left, you need like, so you need this to be smaller. So on the left, you need everything to be smaller. So if the max element on the left is smaller than the roots value and the minimum element on the right is greater than the roots value, then you know that this is correct. So these are the two things you need to carry from the left. That is max value, min value, and also the size of the whole tree. So left count and right count plus 1. That's something. Also going to be recursive. Flatten BST to linked list. There's something we need to like solve again. I did solve this, but I want to solve this again just to be sure. This is also recursive, and it's mostly having a previous so like initialized to null and then going through the root and recursively, and then when you come back, you assign roots right to previous and roots left to null. So you keep doing that recursively, and previous equal to root. You keep doing that and that will work. We'll need to solve this again. Median from running data stream. So there's like two heaps, one min heap and one max heap, and you need to like store, let's say, whenever you get a new value, you store it in the min heap. So you stored one value, you stored two values. Now there are two values in the min heap and just nothing in the max heap. So it's unbalanced, right? So one of these values needs to go into the max heap. So you pop it from the min heap and you put it into the max heap, and now the heaps are kind of balanced, and that's okay. So for this, you need to get the median, the minimum of them, right? Yeah. And let's say if it is unbalanced, if there's a 3 that comes in these two heaps, you need to get the minimum of that and the maximum of the second one, and then divide it by 2 to get the median. Let's revisit this in some time. Count distinct element in window. Um, this should be a hash map solution. And here is where I came to know that there's something called the delete keyword in Python, which you can use to delete keys from a dictionary. So that's also very important because at every point when we go through the window, like we're having a map of the existing characters in that window, and whenever it becomes zero, we remove that key, and every time we are in a window, like we're leaving that window, we want to calculate the complete total. So for that, we need to get this length of the dictionary of like basically what number of keys, and for that we should be able to delete a certain key. Just putting zero doesn't matter. And next, the kth largest element heap. How to know max heap or min heap and how many to pop. Kth element in a heap. Yeah, so you can either use a min heap or a max heap, and based on that, you'll have to pop or push elements to be able to understand, get the correct one. So if it is a max heap, you keep on, like the size of the heap should be k in that case. So that's that. And if it's a min heap, you need to like pop k to get the kth largest element. And clone, sorry, n minus k you need to pop. Next, I'll be continuing in the next video. Thank you.